This is a shout out to the community because, yeah, things are kind of picking up. There are more and more people and engaging on the forum, and it's pretty exciting. So I thought I'll share a couple of people who've been particularly engaged. And I guess if I would have to pick one person, it would have to be Humble Traveler because he's been super engaged the past month. And also before that, like one responding to other people's questions in a correct way, like people, like especially during the retreat, we were pretty busy. So sometimes someone would ask a question and he would actually come in there and answer that person's question and help people out. People would ask like set up questions for a tutorial and he would try to help them take a look at the error. He also made two pretty detailed in-depth posts. One was about sensor agents of the human body, where he wrote like this really detailed and long post of different receptors in the human body, and there are like all these drop-down menus with more tables and like a pretty in-depth review. And then another longer post about exploring different coordinate systems. So basically alternatives to Euclidean coordinates, so cube coordinates, hexagonal lattice, truncated octahedron, and kind of looking into those and comparing their complexities and advantages and drawbacks. So yeah, just spent a lot of time there. Niels also spent a lot of time responding and kind of looking into these ideas and suggestions. And then, oops, so end of January, Will posted this post about getting feedback from people and input on our plans for the robot hackathon. And there were a bunch of people who made some really interesting suggestions, posted pictures of their projects and ideas. One that was particularly fun was Data suggested Monty on the moon, basically doing time sharing on one of the moon rovers. But yeah, there were also a bunch of other people who commented. Rich Moran, he's been active on the forum pretty much since the beginning. Raleigh also has been active a lot the past months. And then there was a really nice and detailed post with a lot of good points from Miguel or Daniel Olivar. I'm not sure how to pronounce it, but it's been like, yeah, a lot of good points there on how to simplify robotics projects, how to use existing libraries instead of reinventing the wheel, and making sure it can be done within a week. So yeah, this whole thread was really useful, I thought. And then there have been several people who posted for the first time and interacted for the first time. So here's Dunehammer asking about like generalizing learning modules to more abstract spaces. And there's been a lot of conversation there. Hoj made her first post response here. And then we also had a familiar face comment. Let's see if I can find it. It's been a long thread, at least familiar to some of us. Rick also commented here since he knew John and Niels, and just kind of trying to translate between the different languages and backgrounds. If you remember Rick from Numenta. Yeah, and then Kate posted about if there's a hosted version of Monty and why that might be useful. There was a post about compositionality by Eli, first time he posted there. Again, one where Humble Traveler came in and answered a lot of questions. And then on the community involvement post from Will, there was a guy, Zach, who posted that he would like to build a robotics project as his undergrad project using Monty, and a bit of back and forth there of what could be done there within the scope of an undergrad project. And then, yeah, subsequently started a new thread about in our projects category, which is the first one there. Yeah, so nice new faces. And then contributing code, Jeremy started getting into the Getting Started guide and then ran into an issue that had previously been posted on our issues page, and then actually did a pretty deep dive into this issue, kind of suggesting ways we restructure the code, making a longer post on the forum there, asking about more context, and then actually opened a really nice PR for it, using a context manager for the Monty experiment, which, yeah, we're going to merge. And yeah, even like followed up with some other people from the community who asked questions here and going into depth about what he's learned so far about the code. So that was a bigger code contribution. And then also documentation contribution. We had from Matthew Stern. He made some really nice like drawings or designs that are now in our documentation on the vision page. And then lastly, also, like, I mean, it's also contributing just to share our project and share our ideas on social media. So I just thought I'll highlight a couple of posts I saw the past month. I'm not going to read through it all, but there were pretty nice posts about how the project is a nice alternative to LLMs, a radically different and more ecological approach to this whole challenge. Very exciting. Yeah. There's another one, like they will not reach AGI, which not only means it can do anything, but also that they know how to learn. It's about LLMs. Here's what will get you there. And then sharing the podcast on the Jim Rutt show. And this one was a longer post as well about how the project is challenging conventional AI, inspired by the human neocortex, and just kind of talking about how it's an exciting alternative approach. So also, thank you for these people sharing our project with their network. So there are several things I can go over. One is, I guess, the figures and stuff in the white paper. I mean, everyone of the research team should be very familiar with them and how it works. So if that would be helpful, I can go over them so you know how to explain them to someone else too. Another thing I thought would be kind of cool to start off with is a bit of a history lesson on the graph learning module, because I feel like it gives some of the background that you wouldn't usually get, but it helps frame some of the discussions we often have, like the displacement matching versus feature set location matching kind of question. So I might actually start with this one if no one has an objection. And then the last
I think that's a
thing,
good idea, actually.
yeah,
Yeah,
okay.
also because the code, that's kind of how it evolved, and yeah,
Yeah,
in
and yeah,
general, I
it's
think
still
that's
in
useful
the code.
context.
So
Right.
yeah, and you'll come across stuff from all of them when you go through the code. And then yeah, lastly, definitely want to go over like the evidence graph LM code, at least like this part of what attributes we have and how they actually interact with each other and affect matching. So yeah, I started like a blank Excalibur draw just in case people want to like ask questions on the whiteboard or I need to draw something. So I'm just gonna share the link in the Slack coding channel if someone wants to join there. So yeah, let me start with a brief history of graph matching in Monty. So this is a write-up. It's on Overleaf, but also the PDF is in our Google Drive. Basically, we have three types of learning modules in Monty at the moment. We have the displacement LM, we have the feature LM, and the evidence LM. So displacement graph LM uses edges in a graph. Hang on, let me see if I have the graph picture in here. Here we go. All right, so this is a graph. I think you're all familiar with this. In Monty, we define graph as nodes at locations. Nodes have features stored at them, which can be like point normals and curvature directions. Those define the pose of that node. So like the point normal and the two orthogonal curvature directions basically span up a local reference frame for that point and thereby define the orientation of that point. And then they can also store other features like color or curvature amounts. And then we can have edges in the graph, which are basically connections between the nodes. Edges, there we go, some older plots. Edges can be built up in different ways. You can either like lay them down as you're sensing, so they are put down in the path that you're going over the mug, or the kind of default behavior we had was nearest neighbors. So each node would connect edges to its nearest neighbors when we add a graph to memory. And so when we do matching, we always get a sensation and then a movement and the next sensation and a movement and the next sensation. And we get those relative to the body. So we get a location relative to the body, movement, next location relative to the body, movement, and so on. And so when we try to recognize an object, we can either take these movements and try to match them to the edges stored in the graph, or which is what the displacement graph LM does. Or we can take our nodes in the graph as initial hypotheses and then test the movements as hypotheses and then look at the location where we end up at. Don't know if that was the clearest explanation.
Maybe it's worth describing that point pair feature thing that was used for the displacements, because
yeah, let me draw
the
on the board.
because like the displacements weren't like, you might think of displacement as like just a vector, and so it's like, oh, you're just matching this movement vector to any one of these edges, which is just a vector. But they were more specific than that. The displacements were basically a line connecting two reference frames, and that was this kind of rotation invariant structure. That's the displacement. So it's a lot more specific than just like a random, or than just like a movement.
Yeah, let
And
me
so
change.
if you see PPF in the code, point pair feature, that's what that's referring to, that kind of 3D structure.
Yeah, so basically, let's say we're in the world, we have this blue cylinder. Can you guys see what I'm drawing on Excalibur? I should probably. Oh, I can't even see what I'm drawing. Ah, here we go. Maybe I'll share it like this. Okay, so we're seeing this blue cylinder. Our sensor is, let's say, here, and then our sensor moves to here. So now we have two locations, and we have a displacement between these two locations. So now, how do we use these two locations that are relative to the body in order to recognize this object, which is stored in the model's reference frame? One option, which is the displacement matching LM, is we take this displacement that we observed and we try to compare it with all of the edges that are in the mark. So it might be this one, it might be the other way around, it might be here. It could be this way, flipped around this way. So we can compare it to all of these edges that we have stored in the graph. And then over time, we sample more and more displacements, like a chain of displacements, and it becomes more and more unique of where on the object we might be. And like Niels mentioned, this has a really nice property because, as we found out, is if our points in the graph have orientations like this, and we have a displacement between these 2 points, we can represent this displacement in an orientation invariant way using point pair features. So basically, we can have a unique description of this displacement that is independent of its orientation. So if this displacement is observed anywhere in the world at any orientation, it will have the exact same values. It's basically the length of the displacement and then the angle, so it's the length and then the angles between, I think, some of these points here. I forget which ones exactly. It's described in this paper, I think.
And just to remind myself, I guess that this assumes that the reference frames for the local points at either set are unique, as in like if they were ambiguous about a certain axis or something, you would still need to like sample multiple hypotheses kind of for different rotations.
No, you never have to sample a rotation hypotheses.
But what if you it's like not like what if it's symmetric? Like often we don't actually know like if it's based on principal curvature or if there is no principal curvature, then you just have the point normal.
Oh, yeah, if the principal curvatures are not defined, then yeah, you can't uniquely define the point pair feature.
Right.
Like,
Or even when they are defined and they're symmetric, like they're mirror symmetric, then they would almost be 2 point pair features, either 2 point pair features
yeah,
stored, or you would test them under like those two hypotheses. So
yeah,
I guess it
that's
like it
right.
reduces the space, but it in practically it cannot totally eliminate the need to test multiple hypotheses of rotation.
But you would basically just store two edges in the graph if you have like, since we can't uniquely define the curvature directions, we would just store 2 point pair features for every edge. Or if there's like, if we're on a flat surface and we have no principal curvatures are equal, we would just define like 8 or 10 pair features for that edge. But then at recognition time, we don't have to cycle through hypotheses. We just have to compare to more point pair features in the graph.
Okay, so we've kind of stored all possible hypotheses in the graph.
Yeah, 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 exactly.
Anyways, sorry, it's a bit of an aside, but it's not what we're
Yeah,
talking about.
but yeah, so this approach, that's a really nice feature because we could recognize objects independent of location, orientation, and scale without cycling through hypotheses, which we have to do with the current solution that we have. So the current solution that we have is features at locations, um, where basically we start out with saying, okay, I could be here, or I could be here, or I could be here. All of these become hypotheses. Actually, we would probably not say these three because there we would detect like an edge as a curvature. So since we're also detecting features, we only look at the ones that are consistent with features. So we might say we are anywhere around the cylinder. Um, oh, as if a delay. Okay. And then we take the displacement that we sensed and we start at the point where the hypothesized location would be and apply that displacement. And then that becomes the search location. We look at the search location in a certain radius around that search location. We find the points stored in the graph and we compare the features that are stored at these points. And we would do this for any of these hypothesized locations, and for each location we have some hypothesized orientations too. So here we might say, okay, let's look here, but also let's look in the other direction here. And some of them might end up totally off the object, and some of them might, hopefully the correct ones would always end up on the object, and you would observe matching features there.
A question. The displacement one, you said it's agnostic to scale. I didn't get that because I think you also mentioned that the displacement, like the length of the displacement is important. So if it was like at a different scale, then like how, I think that the length would be different or no?
Yeah, so basically how we did in that case, so I will get to the big drawback of this. And given that drawback, probably when I explain this solution, you will see the big drawback already. But basically what we would do is we have like a bunch of displacements stored in the graph, and then we get, like, some of them might be longer, some of them might be shorter. And then we get an incoming displacement, and we would just scale it to the length of each of these, and each of those edge hypotheses would have a different scale factor. And then when we get the next hypothesis, we would apply that initial scale factor to it. So if we started with this one, then the next one would be like super scaled over here, and it would not match this short edge here anymore.
So you're making use of the fact that they're all scaled by the same parameter, which
Yeah,
is
exactly.
you all get scaled the same way. Cool.
Yeah. Yeah, so it's not the same as orientation, where like the representation we use for it is just invariant orientation, but basically we can just have one scale factor for each edge and keep applying that for all subsequent displacements. Okay. The last iteration, the evidence-based LM, is very similar to the feature at location LM. The main difference is with the feature at location LM, we would, like, if we test a hypothesis and then like we look here and there's no feature observed, we would then eliminate that hypothesis from the possible hypotheses. And that was kind of brittle with noise. So we transitioned to the evidence-based LM, where instead of just eliminating a hypothesis when we get one inconsistent observation, we instead keep like an evidence count for each hypothesis, and we increment that evidence count with every step. And then there were kind of iterations on the evidence LM where we made it just a lot more efficient and added extra features to it. Like in the beginning, we would test every hypothesis at every step in a giant for loop, and it would take like 10 hours to run, like an experiment with 4 objects. So then we vectorized everything. Now it's all matrix multiplications, and we only update the top 20% of hypotheses at every step, or top 80%. Yeah, those are some bigger updates to the evidence matching.
And yeah, and I think that top 80% had probably a pretty big, like, I remember you found it had a big impact on the like the runtime. And it's again, I think kind of like what we were talking about earlier, because it's not fixed. It doesn't mean that 80% of possible points are always going to be tested, in which case by definition it's only going to reduce the compute by like a fifth. It's like anything that's within 80% of the max, which might only be 10% of points. It might only be 2 points on an object that are that close to the max. And anyways, yeah.
Yeah.
Just in case wasn't clear to anyone how that produces it.
So it feels like at the beginning
Yeah.
of it, it will be those points that will be tested will be a lot, and as you
All,
narrow,
yeah, all points will be tested basically. Yeah.
and then as you narrow down, it becomes
Yeah, it gets fast very quickly. The first step is still quite slow, usually.
I have a question.
Yeah, so sorry, yeah, go ahead.
Just sort of targeting some of the code bits specifically. It seems like in the code that the rotation for each location doesn't change. Am I wrong about that?
What do you mean with the rotation for each
So
location?
there's a field for like locations, a field for locations, rotations, evidences, and things like that that we save with like the detailed logger. And
Yeah,
when you save at the end of an episode, you get, an evidence count for every per location per step. You get locations per step, but we're only seeing like one rotation per location, and it's not on a per step basis.
yeah. So
So
that's because our hypothesis is always talking about the orientation of the object. So basically, we have, well, maybe not green, let me. So we have our hypotheses, and there we have location on object, orientation of object, and evidence. And so then we have like tons of hypotheses. We might say, okay,
Maybe
I
just
could.
sorry, scroll down slightly on your computer
Oh, sorry.
if people are watching on here. Nice. Like
Um, so for example, for the location, it might say, okay, I might be here, or I might be here, or I might be here. And then for the orientation, it's global for the whole object. It might say, I think the cylinder is upright, or I think the cylinder is 45-degree oriented, or I think the cylinder is like 90% oriented. So as we move over the object, the location where we hypothesize we are on the object will change, which is why this changes over time. But the hypothesized orientation of the object is not changing. Because if the sensor is moving over the object, we still assume the object has the same orientation no matter where we put our sensor on there.
I
Does that make sense?
think so.
yeah, so like it's not an orientation of that feature. Or like
Yeah.
it's an orientation that impacts that feature, like that point normal, for example, but it's not like specific to that particular feature that's being sensed there.
It's not like we're trying many orientations at each time step, or are we?
We are in parallel because you'll have
Yeah,
all these
so
different hypotheses initialized, and you're like assuming you're maintaining all of the hypotheses and you're not like eliminating them through like that evidence percent threshold or whatever. Like the whole episode, you're going to be like, I have that one hypothesis that the mug is upside down. I'm going to move all locations. How does that fit with that kind of hypothesis? I have this other hypothesis it's at this angle. How and integrating over that.
Mhm.
Um,
Okay.
and then yeah, and so they're basically, and that's kind of the issue that Rami's kind of identified and kind of is working on is the fact that like that makes our pose hypotheses very dependent on the first sensation
Mhm.
because like if we sense a surface and we know a surface can be oriented a certain number of ways with the object model we have, but like one way, if I'm sensing a surface here, one of my hypotheses is not that the object is like here or whatever. It might be like rotated about this axis,
Okay.
and that's what kind of determines the initial hypotheses.
I see. I think I
yeah,
understand. So this is where we sort of sample 8 around a rotation, and we try to select, which one of these is most
Exactly,
like aligned with the first observation.
exactly.
and so in most of the cases, like with this can here, we would be sensing, we would have the first sensation, which has a pose defined by the point normal and curvatures. And that pose gives us usually two possible orientations, basically saying, if I'm on this location on the can and I'm sensing this curvature, the can is either upright or it's upside down, because I'm sensing this curved surface, and there's no other way I could sense that on this location of the cup. Like if the can was turned 90 degrees, then the first principal curvature would also be rotated 90 degrees. And so, yeah, the only exception to that is, like Niels mentioned, if we're on a flat surface or a circular surface, then the principal curvatures are equal. So they don't tell us anything about the directions in which they point.
Okay.
And then the nice thing is, even then, we don't like uniformly sample all possible rotations of the object. Like if I'm
Yeah.
sensing this, although
Right.
it could be rotated about this axis, I don't sample this as a possible hypothesis, this is a possible blah blah blah. That is something you can do in the code, which I think is called uniform hypothesis sampling.
Yeah.
But even then, in order to make that tractable, it does it at increments of like 30-degree orientations or something like that. So in practice, it doesn't really do a great job, as well as being computationally expensive.
Got it.
Yeah, you always have a point normal. So that already tells you a lot about the potential orientations of the object. Okay, so yeah, we have a bunch of hypotheses and we can update all of them at each time step, and we can do all of that as like one large matrix multiplication. Which is what we do at the moment.
So are the hypotheses by default sampled as all of the points in the graph, or are we sampling from the points in the graph?
Yeah, so right now, the way we initialize this hypothesis space is we add one hypothesis for the location for each of the points in the graph.
Okay.
And then for each of these locations, we add either 2 or I think 8 possible orientations, depending on how the principal curvatures are defined.
Okay. So if the graph is too dense, we'll have too many hypotheses, and if it's too sparse,
Yeah. Yeah, exactly.
Yeah, and I guess it's worth mentioning that when the hypotheses are initialized for that reason, they're kind of on the nodes in the graph. But once we start moving, of course, there's no guarantee that we're going to be on top of like exactly where a node in the graph is, and that's where the kind of nearest neighbor matching starts coming in.
Yeah, and one thing that I guess, we talked about a long time ago is to kind of re-anchor hypotheses. So basically, like you say right now, if the graph is too dense, you have way too many hypotheses, but also if the graph is too sparse, you have too few hypotheses, like what Neil said. If I'm only starting with these points, these few points that I drew in this illustrative graph, but actually my sensor first sensed down here. I'm drawing a green point, but it's taking time to show up. I'm sensing down here, like far away from these other points, and then I'm moving. I will have a harder time recognizing that object. So one thing that could be done is like when you sense very distinct features on an object, like the point where the handle meets the cup, or like, I don't know, some other distinct features, you could re-anchor 2 distinct features stored in the cup. And that could help with that. But yeah, we haven't really gotten very deep into that idea. Just to wrap it up on the displacement matching problem, I don't know if everyone is already aware of it. But basically the issue is, in order to recognize this object, you'll have to sample the displacements that are stored in the cup. You can't sample other displacements. So if I sampled this green point, there's already no chance for me to recognize this cup. Basically, if I move like over here and then over here, like there are just no displacements that match in the graph, so I would just not be able to recognize this object. And that's a pretty big limitation, because in order to deal with that, we would have to have a very dense graph with like an all-to-all sampling of edges, which is just a combinatorial explosion. And yeah, it just didn't seem tractable. One thing we talked about is what we thought about is maybe at some point having a hybrid approach where we store like significant displacements in the graph, like face, you would store like displacement between the eyes and the nose and the mouth. And then you store features at locations, and that way you could very rapidly make like a general inference of the object, like quickly infer a face if you move from eye to nose. You could have action policies that are kind of aimed for sampling these specific displacements. But you could still recognize the face if you made a different series of displacements using the feature at location approach. But yeah, that's where this idea got killed, I guess. So yeah, here's kind of the comparison. So basically, all of the three approaches are location invariant, all of them are rotation invariant, although features at locations need to explicitly test different rotations. Only the displacement model is scale invariant. With these, I guess we could explicitly test scale as well as a hypothesis, but we've never tried that, and it would add a lot more computations, like it would scale linearly. We can sample new displacements with this one. We can do that with the features at locations approach, because we have like a reference frame of locations that we can interpolate between. We can sample new locations as well. Like we don't have to sample the exact nodes stored in the graph. We can sample any on the object. Dealing with noise was only really possible with the evidence-based approach. And another nice advantage of the evidence-based approach is that it can give you a most likely hypothesis at every step. So with the other two approaches, which are, I guess, maybe a bit more like HTM, you have like a union of possible matches at every step. Like this is all that's possible. And then if you get an inconsistent observation, that gets removed from the union of possibilities. But with the evidence-based approach, you always have a most likely hypothesis. Even if you're not sure what you're sensing yet, you can start making like model-based actions on test hypotheses, for instance. Does that make sense?
Yeah.
Maybe it's worth, yeah, it was really nice overview. Maybe it's worth talking a bit about the transformation of information coming in, because that also kind of relates to the thalamus stuff we were talking about last brainstorming. And I think that's something
yeah.
that can be confusing in the code, is like these kinds of transformations of features and stuff.
Yeah. So maybe I'll just draw up here. How to best explain?
Because I guess
Alright,
to the
so
thing that we were talking about just now, we have this kind of global hypothesis for the rotation of the whole object, that each hypothesis you can kind of think of as like a different, that's like a reference frame. We have an orientation for the object and we're moving through that, and we're getting these features at a pose coming in, but those are initially in a sensor's reference frame.
yeah. So let me make the neuroscience analogy real quick first. And the thalamus, because we mentioned it. So we have incoming location and orientation. relative to the body. And in layer 6, we would have a hypothesis of the object's location and orientation. So that would be hypothesis of where we are on the object and how the object is oriented relative to the internal model of the object. And so that hypothesis, we have this backward projection from layer 6 to the thalamus, and the theory is that backward projection can modify the input that goes to the relay cells and then kind of rotate that input that then goes into layer 4 and other layers. So basically, this is where the transformation would happen between the object's reference frame and the body reference frame. So now, where does this happen in Monty? Maybe I should show this in the code in a moment. But, yeah, I guess to get to your point, Niels, about having different rotations and orientation hypotheses of each object. Can I copy something on Excalibur? Yes, awesome. Okay, so we have all these hypotheses. We have the incoming location and orientation. Technically in Monty, we have the buffer which calculates the displacement. In the cortex, we might just get the displacement as input. But yeah, for a moment, let's just talk about location and orientation that comes in. So I'm waiting for my iPad to update the drawing. But so basically we have one sensation, it's in body-centric reference frame, and we have all of the hypotheses that we want to test. And what we basically do is we take this one sensation, we multiply it with this large hypothesis matrix, and we get an output of all the new hypotheses test. This might not be so easy to draw. Maybe I'll just go to the code for it.
Yeah, and like I don't know if it would be helpful if we can make it more concrete in terms of like, say like with the sensor module, it's getting a depth map, and then it's extracting this point cloud, and then from the point cloud it's extracting point normal and principal curvature directions. So that's going to be a location and like a mini reference frame. But then we're kind of combining that with information from habitat about where the sensor is. That's the sort of body-centric location, I believe, that we kind of start with.
To get the body-centric location? You mean?
Yeah, as in like the
What we do in the transform?
location that's actually passed in.
You mean what we do in the transform?
Yeah.
Depth to 3D location transform?
Yeah, like the coordinate system, when we say that's body-centric, I think it's really kind of habitat-centric or...
Yeah, I think, yeah, in this case, it's relative to like the origin of habitat.
Of habitat. Yeah, it's
Yeah.
like it's an external kind of coordinate system, but in a robot, it would be kind of relative to, you know, the torso or the hand or something like that.
Yeah, so there's this variable called world coordinates, and you can turn it off and on. So yeah, whether you want it to be in world coordinates or not. And basically what it does, if it is in world coordinates, it takes into account it gets the sensor locations and orientations and agent location and orientations in the world, and then applies those transformations to the point cloud that we're sensing to turn them into world coordinates, or like basically to calculate out the sensor and agent movement from the point cloud that the camera image is getting. Because from the
Yeah,
camera,
and
we
which
basically get the image, and that doesn't tell us where in the world it is at all.
yeah, and then but then I guess the nice thing about Monty, because it's using an object-centric recognition system with movement, we don't need to do that. You could just have like the location could literally be in like the coordinate system. Like it just needs to be consistent across movements. That we know the orientation of the sensor and that we have the movement information. Like if my incoming location is like if my location and orientation is relative to my fingertip, I feel something here. As long as I have a movement, the location doesn't really matter, but the orientation is what needs to be kind of tracked. Because we're going to integrate it in like an internal reference frame.
You're
I'm
talking
pretty sure
about
that's
like it's not to just send displacements?
yeah, displacements and orientations. But I mean, it's not displacement. It's like movements. It's not like a displacement like we're matching an edge. It's just like we've moved through
I mean, a
space.
displacement to me always includes location and orientation changes.
Yeah,
So like if I'm just talking about location changes, I would say translation. But displacement already includes an orientation change. Like if I rotated my finger and moved it,
right,
that would be included in the displacement. But yeah, I mean, we talked about before whether we can just communicate displacements instead of locations in a common reference frame. And there are these issues with it where like it'll make interaction with the environment very difficult
right.
because you don't know where in the world you are.
Yeah, and like voting and stuff like that. No, that's true.
Yeah. But yeah, I think that's more on the like sensor module stuff. So yeah, maybe I'll focus on the evidence module for now, and then we can
Yeah,
get back to that sometime. But yeah, I think we talked about it before also in the sense of like whether that's maybe a difference between the where and the what pathway, that
right,
the what pathway does access to body-centric coordinates. For common coordinates, it just gets displacements maybe. But yeah, I don't know. That's
right.
very speculative.
But yeah, so I guess in terms of the code in general, it's this world coordinate thing, which is just like a common reference frame.
Yeah. So yeah, we get these locations in a common reference frame. And then we call update possible matches, which loops over objects in memory. We use multi-threading for this in most cases. Since we can update the evidence for each object in parallel, they're totally independent. The brain could do this in parallel too. And we call update evidence. The doc string, I guess, helps explain everything a bit. We basically start with 0 evidence for all of the hypotheses. So a flat prior could be different in the future. Like if I'm in the kitchen, I kind of have some priors that I will see certain things there, and won't see certain other things. But we start with 0 evidence for everything. And then the features and displacements either add or subtract evidence. I think this should say pose features. And then features like color can only add evidence, they can't subtract evidence. That way we can recognize the same morphology in different colors, kind of. And then evidence is weighed by the distance of hypotheses to the point in the model. There are also votes, which are handled somewhere else. And here, this is kind of the point of maybe at some point we do a hybrid approach where we can also use displacements to infer like an object's orientation more rapidly. If we're on the first step, we initialize the hypothesis space and initialize the evidence using the first observed feature. Otherwise, we update the hypotheses. So that's what we do here. So if the displacement is none, so we have not moved yet, we basically call get initial hypothesis space. To get that, we use the features that we observe, which are like the point normal and curvature direction. And we update the first evidence for it. The more interesting part, that's what we mostly do, we have actually moved already. So now we go here, we have a displacement, and we do a couple of, yeah, all right, so we, this is a bit detail on like the different input channels. But basically, this is the interesting part. We have all of these possible poses, which are orientations. And in order to test this displacement, we have to rotate the displacement by each of the rotation hypotheses. So basically, this is a matrix of different rotation matrices. And we multiply, like we take the dot product of these rotation matrices and the incoming displacement. And then we have to calculate the search locations, which is where in the graph do we want to check the stored features? Where might we be after this displacement? In order to get those search locations, we take a location hypotheses and we add the rotated displacement to it. So yeah, let me draw this real quick. Or maybe I can just point it on the screen. So, you know, I think
There was also, yeah, I was
this.
gonna say there were some figures in the paper that might be worth using.
Yeah.
So that list of possible
Okay.
poses, that is changing, right? On each time step. And or
No, possible poses stay the same at every time step. Only the evidence for them changes.
okay.
But possible locations update. So basically, possible poses is just used to get a list of rotated displacements. That's like a temporary variable that we only use in this step. Self-thought possible poses is not modified. And then we calculate search locations by taking the possible locations and adding the rotated displacements on them. So basically, we have an observation here, this pose, and a displacement. And we have all of these possible locations on the cylinder that we could be at. And we take this displacement and we rotate it by the pose hypotheses and add it to that location. So hang on, this is the first step. So this is just initializing it. It doesn't show the search location. But then we have these, like we have initialized a pose hypothesis for every location on the object, or several of them. Like this point has two possible orientations of the object. If I'm at this location in the cylinder, it's either right side up or upside down. And then we get the displacement. We use the displacement to rotate. We use the pose hypothesis to rotate the displacement. We add the displacement to the hypothesis location, and that's the search location. So you can see here, if I was at this location here, I hope you can see my pointer. If I was at this location here, I might now either be up here or down here. And if I was at the top of the cylinder, there are more pose hypotheses. So there we have like these kind of circles of where we might be next. And that's why in like these animations, the search locations or the hypotheses can go kind of off the object, because a lot of them will be wrong. And a lot of them, when we actually apply the displacement, will end up off of the object. And then we look at the features stored at these at these search locations. And for instance, if they're actually off of the object, that's negative evidence, it's low likelihood. If the feature doesn't match, that's like the color is wrong, that's no evidence for that. If the color is right and the features are right, that's high evidence, like here. And then we do the same thing. So now we moved actually like sideways. So again, we have all of these different hypotheses of where we might be and what the rotation would be. We apply the rotation to the displacement, draw a line here, give us the search locations. At each of these points, we look in the graph. How do the points stored nearby in the graph compare to the observed features? And we use that to update the evidence.
Do we compare to the average of these points, the closest KNNs, or do we compare to just the best one?
Yes, good question. So basically, we have a search radius. So here's the example of hypothesis that we're at this location. There are two orientations. We have this displacement. We rotate the displacement by the pose hypotheses. We get two possible locations. And for each location, we look in a certain search radius. We look at all the points in the radius and update the evidence. Like we calculate the distance between the search location and the point in the graph, and also the feature difference between the points in that. And that gives us kind of an evidence value for each of the points in the radius, and then we take the best match within that. So the maximum value.
Okay. Does it do any better if we do with the average, or like?
No, it does worse with the average, because the point is, like, you might be in an area on the object where features change quickly, like right before the edge of the mark. So you'd actually get quite negative evidence if you compare it to the points in the graph up there. Or if you have like a very flat object, you might actually have point normals that are opposite stored in that search radius. You don't want that to drag down your evidence. If there's something that matches your observation in that radius, that's evidence for this object.
Okay, that makes sense.
And so when you do find that you've done a displacement, you find a point that matches nicely, which location has its evidence updated? The one you left from or the one you arrived at?
Yeah, so
location by location basis, right? So
yeah, so basically this row here in the hypotheses, the possible locations on the object, gets updated at every step. So with every displacement, we update where we might be on the object. So basically this evidence keeps count of, like, basically evidence for path that we took on the object. Or yeah, to answer a question, it would be the evidence for the location that we ended up at. So
Okay.
the evidence for that we actually are at that search location that we tested.
And if we did kind of something like re-anchoring, it might be changing the location to the point where we get the maximum feature match,
Exactly, yeah. Yeah, that
rather
would be
than
how
our location being sort of like the point somewhere in space that we think we are after path integration.
yeah. There are some more detailed things. I think, yeah, it's in the documentation, but not in the paper. But basically, the search radius can be informed by the sensed curvature. So if we have a very flat surface that we're sensing, we don't really need to sample points in like a circular sphere. We can sample points along the surface only. So we can use the point normal that we're sensing to kind of inform whether, like, we can use the point normal to squish the search radius from a circle into a sphere that is like going along the surface of the object. If that makes sense. So basically, we're like how we do it on a technical level is we adjust like our distance measure, like the way we weigh the distance from the search point to other points in the graph is being squished by the point normal direction.
Okay.
So here, if we threshold, like on the flat surface, we would get only points in the graph that are actually on the surface, and then if it's like a round curvature, then we do more of a circular search. So then we have all of the search locations. Then this is where we do the evidence update thresholding. That's the part that's for efficiency, that we don't need to actually update all of the hypotheses, only the most likely ones. So get a threshold, this is where dog was. We get hypothesis IDs to test. And then, yeah, if there actually are hypotheses to test, which might always be the case, if it's an object that's already very impossible, we will not test anything. We will then get the search locations that we want to test. And yeah, we calculate the evidence for these search locations using the features that were observed. I give us evidence. We clip that evidence to not be smaller 0. And yeah, basically add the evidence to the existing evidence and weigh it by like the past weight and the present weight. And that's the part, Rami, that you played around with last week. Basically, if past weight and present weight add up to 1, then the evidence is bounded. It will never go outside of the range -1 and 2. If past and present weight add up to more than 1, it's unbounded. In the current default setup, both are set to 1, so they add up to 2. So evidence can grow infinitely high in theory, which basically, if we bind the evidence values, we have like a finite memory horizon. And with the current action policies, that doesn't work so well because basically the memory horizon is too short to actually explore a large part of the object or to actually sense the whole shape of the object. But eventually, I think this is the more elegant solution and how the brain must be doing this, because yeah, neurons can't fire infinitely much. So, or like you have like hysteresis, which is bounded, I would say. But yeah, I think this only like a bounded evidence values only really work well if you have like either very efficient action policy or some kind of replay of past significant features or something like that.
Yeah, and maybe with like hierarchy as well and more unique features, that would help as well because like
Yeah.
right now everything is kind of sensing point normals in kind of local surfaces, and so yeah, even if you jump to the other side of an object, you're still going to feel a point normal. Like the displacement will be different for different objects and stuff like that, but it's still not that unique. It's not like you move somewhere and it's like, oh, this is a handle and something very yeah.
Yeah.
In general, it fits well with Will's strategy during the TBP Olympics that you want
Yeah,
to
moving
move
very fast.
quickly if you're not getting very good features coming in.
That's right, yeah. So yeah, I feel like there's a lot more to cover, but I've already been talking for more than an hour, so I don't know if we should take a break at some point and keep going at some other point, or if you're gonna ask some specific questions. Yeah.
Does it ever happen that the search radius doesn't have any points to test? And how do you handle that? Like you get
Yeah,
double,
it does.
you
Yeah,
just
it's
don't have any.
basically if you end up off of the object, there'll be nothing in there and you get -1 evidence.
But you
See
could
if I
be on
can.
a very coarse model and you're not off of the object, but you're on the surface, but the model is too coarse.
Yeah, so that's why you have to kind of set that. So we have this parameter called max match distance, and that's basically like the radius of the search thing. And it's usually set pretty large. Like for the coffee mug, I think it's like a fifth or something between a fifth and a tenth of the height of the coffee mug, as far as I remember. So it's like definitely way bigger than the distance between points in the graph. If you set that too small, then that problem can definitely happen. But so basically, as you make the graph more sparse, you would have to, if you make it too sparse, you would have to increase the max match distance, but you would have to make it very short for that.
So ideally, we would want to make it as a function of the coarseness or the sparsity of the points in the graph.
Yeah, that could be a good idea. Yeah. Yeah, that's actually a great idea. I've been kind of trying to start thinking about like if we build a platform for this, we don't want people to have to adjust all of these different parameters and understand them. How do we simplify this thing? So yeah, making the max match distance just a function of the sparseness of the graph or this distance between points in the graph, that would be, I think that would work well.
It also could be a learned thing, right? Because, each object could come with its own distance because you're only matching what you learned. So once
Yeah,
you learned and determined, at that point you determine what the distance is, and that for you always use that distance for that object.
right. Yeah. Yeah, so yeah, I think it would make sense to have that like an object specific parameter probably, or at least like yeah, something from the object model function. One topic I didn't get into at all is like the object models and constraint graphs versus unconstrained graphs. But that's another topic. But basically, we have already other parameters for graphs, like how large can they get size-wise, how how many points can they have at max, and what else? Yeah, how much spatial resolution can they have at max? So the max match distance could be based on one of these parameters as well.
So one more question. I noticed that the evidence is split. It's split by the graph IDs, and that results in the need for this for loop over the objects. And I'm wondering if it's more efficient to vectorize everything and have something similar to the channel mapping hypothesis, whatever, just to know which hypotheses are for this graph ID, like something separate, and basically just have vectorize all of the evidences. Would that make it more efficient, or what would be the problems in doing that?
Yeah, that's an interesting question. Off the top of my head, I don't see an issue with doing that.
Sorry, Ron, can you repeat the question? Vectorize the evidences for
No, now
that part.
So now we have to do this for loop over all of the evidences, and then we're just updating a graph ID by graph ID.
Right.
I think we're doing it parallel, but it seems like it would be more efficient to have all of the evidences in one vector, and then we can just apply. So basically, when we think about hypotheses, they'll only be in one vector instead of separated by the graph ID, so that we don't have to loop over them. It's the same efficiency step that Viviane took to go to basically she went one step into grouping all these hypotheses together and making them one vector, and then applying the transformations on that one vector instead of a for loop. But now we're doing it another step where we would have all of the graph ID hypotheses together in one vector, and then we could just apply one transformation. We wouldn't have to do this for loop for the graphs. It will be especially helpful when we have a lot more objects. We wouldn't have to loop. Does that make sense?
Yeah, I guess in general, I mean, the like, what if the number of objects changes? I guess would it still work? Then, if so, then I think it makes sense.
Yeah.
Yeah, it's basically the same cases for the input channels. I never noticed the parallels because I did those things at totally different times. But yeah, like Rami says, for the input channels, we basically put all possible locations and orientations for all of the channels into one large vector, and we just store the mapping between them, like which IDs correspond to which channel. And if we add another input channel, like the case that we mentioned, that Rami mentioned earlier, where we add a hypothesis to the hypothesis space or an input channel, we just append to all these lists, to the mapping and to those. And we could do the same thing for over graph IDs as well. I don't know if at some point, like hardware-wise, you run into some limits. You don't want to do the matrix multiplications that large anymore. But yeah.
Yeah, I don't know. Yeah, I think especially if we're using GPUs at some point, then probably the bigger the matrices, the better up to a limit. And
yeah, I guess question what that limit would be.
yeah. Yeah, and I mean in general, I think resizing tensors is not as trivial as like appending to lists, because it needs to reallocate memory. But actually, I don't know, maybe it's fine. But yeah, I think we could definitely explore something like that at one point to accelerate it further.
Yeah, then we could do multi-threading over learning modules instead. Interesting idea. Yeah.
It would be a two-level mapping instead of that. So we'd have to the graph ID, and then from the graph ID to the channels, or like we just have two separate mapping.
Yeah.
Yeah, and I guess right now with like the only testing some of the hypotheses, that kind of dynamically builds smaller kind of vectors, right? That we then update.
Yeah, basically we have the evidence threshold, which gives us hypothesis IDs to test. And then we index with these IDs to get a new list of search locations.
Create a new, yeah.
I guess that would be a bit problematic. We would then, if we do it for all of the objects in the same thing, we would then have to separate out the search locations into the different objects reference frames to test them. Or we would
Yeah,
have to
so we
have
don't
one
have like a
giant
ragged list, kind of a ragged array. Because each one would have a
No.
different number of locations.
Yeah, I mean, we would have to separate them into separate arrays, so maybe at that point it wouldn't be more efficient anymore. I mean, alternatively, we could do the kind of biological whatever way where we have one giant reference frame and they're at very far locations from each other.
Yeah, and like a fixed capacity almost, or
Yeah. Yeah, I think it would be a bit more involved than just applying the same mechanism as to the input channels.